First thing. Yeah, friend. Okay, so we're gonna start a new topic today, but I want to go. Oh, one other thing.
Then you don't
Before you hand in your homework, there was I think some confusion on intensity and whatnot. So I want to hand this back and then go over a couple points, and I want to start a new topic. I want to talk about crystals and Bragg diffraction. And what I'm going to do is I'm going to put in significantly more detail than it's normally done in modern physics. We're going to study something referred to as reciprocal space. And I want to show you exactly what the reciprocal space vectors are. And then I want to show you then how you can actually use this and to actually determine the spacing between any type of Miller planes. So that's certainly beyond the scope of this course, but we're engineers that take this course, and that's why I have to study the toss this in here. So that said, let me hand out this homework, and then I want to go over a couple things. Well, thank you. There's no
I should say this is the one. Yes. How this is so why do you want to do that? I don't know. Yeah, I still didn't want to do that. Just
okay. Let's go over a couple points here because I think there's some confusion on these points. Okay, so when we talk about the intensity of light, and so if I were to say just describe what intensity of what means, does it refer to? It refers to the amount of energy, unit time, unit area coming into a circle. All right, so this is the amount of energy, unit time, then per unit. We said that for monochromatic light, okay, we said there's two pieces going into it. What are they?
The energy of a photon.
The energy of one photon. This is HF. This is energy of one photon. Okay. Then times something I called N for no good reason. It's actually kind of a bad notation for it, but those things happen. Okay. The traditional symbol is actually a cat on a skateboard. That's actually the traditional symbol. Okay, so but I'm just going to abbreviate that with the symbol N. Good to know. We're learning a lot here. I'm hoping that some of the stuff we're learning is actually true. Again, I'm aiming for at least 2% truth this semester. Okay, what is N? Number of photons, unit time, unit area. This right here, this is the number of photons, unit time, unit area. Which makes it pretty obvious why you'd use this symbol. I mean, it follows. Okay, so keep that in mind. Now, when we do our experiment for photoelectric, we plot the current here versus the voltage. Okay, what do we call this point here? That's your stopping potential V sub S. And this part where it flattens out is called the saturation. Yeah, so this part right here, this is your saturation current. And our main equation that we're dealing with is what? Your main equation is, remember, here's our metal. So here's a little electron in the metal, and here's a little photon. What is the photoelectric effect? Photon comes in and is absorbed by the electron, and it's liberated. Okay, and we apply conservation of energy here. So the energy over here is what? Just the energy of the photon, which is our gamma here. So this is just our HF. Here's our final energy. What is that final energy over there?
V squared.
Which is your kinetic energy of the freed electron plus phi. And what is phi? Which means, yeah, it's the energy it takes to move that electron out of the surface. Okay, so we have this. We made energy, so this gives us our HF equals 1/2 m v squared plus phi. This. Now, with that in mind, okay, what does our and then we did something else. We also know that we could write this as
H times potential, EV.
it's measured in EV. It would also be E times, I didn't hear the first part,
Stopping potential.
times your stopping potential. So this is also your E times V sub S. So I told you we're going to cheat a little bit here, and here's a little cheat. Let's pretend that this phi is small. Now phi is usually small, so that's not a big cheat. Okay, but if this is really kind of small compared to the other things, then that means your stopping potential is directly proportional to F. Does that make sense? So what this means here is that your V sub F, your stopping potential, is directly proportional to it. Again, it's not quite because of this phi here, but we're just going to pretend that's not a big issue. So that means if your F doubles, what does your V sub S do? Doubles. Okay. Now you have to be a little careful here. Again, just say that it doubles. You could say, well, wait, this is a negative value here. So if it moves this way, it's increasing. This way, it's decreasing. But don't. When you translate that into English, it starts getting funky. Don't do that. Just kind of use this terminology here. Now, what does your saturation current then depend upon? What part of this intensity here? Depends on N. Does that make sense? Because if I have more photons coming in per unit time per unit area, that means I have more electrons being freed, and that means I'm going to have a larger current. So this part here depends on N. Part here is directly proportional to N. This part here is directly proportional to that. Does that make sense? And so if you were to look at something like this. So if F, what do you want F to do? Go up or go down?
Go down.
Go down by what factor?
10.
10. Okay. Now, do you want to do N or do you want to do I? Let's do I, meaning the intensity. Okay, do you want intensity to go up or down?
Up.
Up. By what factor?
31.
I heard what? 3. Okay. Let's say. Okay. The question is, if here's the graph. Here's my original graph. I want you to make a qualitative sketch of the new graph. Okay. So 1 point's easy. Which point's easy? The what? The stopping potential is easy. Why?
110.
Yeah, this would have to be, if this right here is for F, so here's your F, here's your V sub S here. This is the original, as I said. If your F increases by basically a tenth here, that means that this has to decrease by 10th. So this point here is going to have to go to V sub S over 10. Now, again, it's not exactly that amount because of that little 5, but let's pretend that that's not a big issue. So this has to go down here. Now, the question is, what does this then do? Does it go up like this? Does it match this perfectly? Does it go down? What does it do and why?
Excuse me.
Yep.
So I think for the question, like concluding like it's decreased by a factor of 7 or whatever, for the stopping potential, it could only work if we neglected that phi.
That's why I said here that we're assuming that this is small. That's what I meant. Yes. Okay. So what do we do? By what factor? Up by a factor of 30. Others, do you agree? Prove it. Okay. So if I give you this, and if I give you this, what would you then have to do? You'd have to find n. So what is happening to n? It has to go up to by a factor of 30. Does that make sense? What do you have here? You know that your I is your HF times n. What's happening here? Your I is going to 3. Going to 3. Your F is going to this guy. And so we have this n new. So my phi n new is going to be what? It's going to really be this 30i over HF. So it's going to go up by this factor. That makes sense? Okay. So what this is going to do here is this, if this is some original factor here, let's call this, I just call this current. This is going to have to go up here so that this value here, this would be 30. Is it correct? Excellent. Again, this isn't going to be quite perfect, but it's going to be, you know, again, because of the 5 there, but it's going to be kind of close. That makes sense? Questions? Okay, so that said, new topic. And since you have to deal with some of these ideas in homework 1, and since there are kind of some mistakes made about daily homework, that's why I extended that, just so you can patch it everything. Okay, so we're going to talk about crystals, Bravais lattices, reciprocal space. Uh-oh.
And then no, COL. No, I don't think so. Yeah, hard. No, they.
So reciprocal space. Miller indices. And Bragg diffraction. It all makes sense. So that's what we want to do. And I think before we go any further, I want you to check markers here. This one, actually. Okay, so first of all, let's start with crystals, and then I want to go into then what it means to be Bravais lattice, and then we'll go from there. So, what is a crystal? And since I'm starting with a question word, I'm going to have a question word. Okay, so what's a crystal? So, in principle, how big is a crystal?
Very small. Very large.
In principle, they're infinite in extent. Okay, so in principle, a crystal is always infinite in extent. Now they never are, obviously. But the atoms are small, so if you look at the size of a real crystal in life compared to like the atoms making it up, it's but in principle, this is infinite. Okay, and more. What's your unique feature?
They have repeating units.
Meaning they are periodic. Okay, so this is basically, it's gonna be basically, these are infinite structures. Okay, that are periodic. Okay, what does it mean to be periodic? Means if I'm here, if I go over some distance here, what does it look like? Same, go over the same distance, same. That's what it means to be periodic, and we want to make this a little more rigorous. Now, what we can do is we can crystal is being composed of two quantities. Okay. The lattice and the basis. And again, you probably know what these words are, but I don't care, and then I'll set these up. So let's start off with the lattice here. The lattice is going to be the part that's periodic. So the periodicity of a crystal is reflected in the lattice. So I'm going to see how far I can go up to here. Go up to about here. So let's just draw something like this. Principle that already can't be a crystal. Why? What is it not?
Is it infinite?
It is not infinite. No, obviously, you can't make these things infinite. So you say good enough. Okay. But you can see that this actually has kind of a periodic. This is periodic here. Go from here to here to here to here to here. I'm gonna make this tighter in a little bit. This lattice here is going to be something referred to as a Bravais lattice, and I'll define what that means in a while. So basically, the periodic points here, that's my lattice. Okay. Now what I need is basically a basis. So this right here is the base. Now I need a basis. And the basis is going to be basically a collection of atoms. Okay. When I was in graduate school, when I was taking my first condensed matter physics class, my professor was actually outstanding. That's the only time that solid state physics ever made sense in my entire life is with him. He said, view the basis as basically a stamp. So view this as a stamp.
You have a good memory.
I remember like, oh, this is what it is. It's great. So he says, view it as a stamp. So maybe the stamp is then going to be a big atom here, and then a little atom here. So I'll call this atom B, and this is atom A. So here, this is my basis. Now, what I would do to make this crystal, so I have this as a stamp. I come over here to this point here, I go stamp. So I put this atom here, these atoms here. I come over here, bam, over here, bam, over here, bam, bam, bam. All I do is wherever I have a dot, I stamp it like that. That's my basis. That now becomes my crystal. Okay, that makes sense? So it's really, there's going to be two components here. There's going to be the lattice that makes it up, and then your basis set of atoms here. Now, what does that mean here? That means something. Yep.
So is the lattice like just like the collection of points you said, right?
They're going to be the points, and then at each of the points, I put my basis. That's
So there's not actually like anything there at all, right? It's just
it has whatever the periodicity of the structure is in that lattice.
it sits in that.
Correct. So in other words, that's what I have here. Now, the lattice I have, and then the basis of atoms I have actually can differ from setup to setup. I could have one atom basis. I could have actually then one set of I could have one lattice here. I can actually change these. So different problems the same problem can have different basis factors. Well, I haven't used that word yet. I better not use that word at all. Basically, what I'm calling a basis here can differ from basically on the same problem here. Because somebody might say, well, I don't want this to be my stamp. I want something else to be a stamp. That's perfectly fine. And then what happens is that then my overall, my picture here actually might change here. So the actual lattice I have and the basis I have can actually vary from person to person. You're gonna still end up with the same crystal. Okay, but what I call the lattice and what I call the basis here, that can actually differ. Okay, but this idea here that your crystal, and I know some people hate this notation, but to me, as long as you realize that it's kind of what it means, you can think of a crystal. This is basically your lattice plus your basis. I know some people really despise this definition here, but to me, I think it's actually very insightful. I'm putting quotes on it because it's not a real equation, but it really has the idea here that basically if you have your lattice and your basis, put those two things together, you now have a crystal. Does that make sense? Now we need some names here. This lattice here, we're going to call, we're going to specify to a certain lattice called Bravais lattice. So let's consider lattices. Lattices that are Bravais lattices. Okay. This is actually he's French, and so this is why it's Bravais. That's actually the correct way to pronounce it. Bravais. And it's going to be the following. Now, I gave you two handouts on the same thing. Let me say a little bit about these handouts here that I gave you. So the one handout that looks like this, that it's all nice and fine, and it says, crystal structures. This is from a standard book in solid state physics by Cattell. Okay, so this is a standard solid state. Let's say undergraduate. Solid state book. Okay, my only problem with Cattell is, boy, he can really describe things in the most obtuse fashion possible. Some of it is very good. But some of the things when he goes to describe things, I can read things that I know extremely well, and I can read it from this book, and I have no clue what he's talking about. So the problem with Cattell is really hit and miss. There can be parts that are remarkably lucid, and then you go on to the next paragraph, and it's utterly incoherent. The other one I gave you is from the other one. It's obviously that I just put my book on here. Oh, here it is. It's actually from a graduate text in solid state physics, Ashcroft and Moon. This is the text I used as a graduate student. This is actually excellent. The problem is it is a graduate text. This handout I gave here is from Ashcroft and Moon. So the other one is Ashcroft. Herman. This is a standard graduate solid state physics one. The reason I gave you say, well, why this is an undergraduate class, why the hell are you giving us this? The reason why is I had nothing else to photocopy this. And I like to always start off my day with photocopies. No, this because actually I think its description on the Bravais, their description on the Bravais lattice is actually quite good. And so what I want to do is to go over here to Bravais lattice. You can see that's when I underlined it when I was a graduate. Learning it, okay. He gives actually two definitions of a Bravais lattice, and they're both basically the same thing. And so what he does here is we're going to use, I'm going to call it the Ashcroft-Merriman definition, although it's not. It's a standard definition. It's not unique to them, but it's good. So there are two common definitions of a Bravais lattice. The first, okay, if you look here, is this here. A Bravais lattice is an infinite array of discrete points. Okay, why does it have to be infinite? Because it is it's a crystal. Okay. Hang on. Okay. Bring my glasses. Okay, this might be entertaining. Okay. With an oral fried in the turkey. No, I'm kidding. Okay, so I can do a little bit better. With an arrangement of orientation that appears exactly the same from whichever of the points the array is viewed. Good grief, what on earth is that? So here's my Bravais lattice. It's infinite extent. If I'm here, my crystal looks a certain way, right? What happens if I hop on this point here? It's identical. What about this point here?
Same.
Identical. So it doesn't matter which point on the Bravais lattice I'm at, it always looks the same. So the first one is going to be that each the surroundings, let's say at any point on the Bravais lattice, the surroundings are the same. Okay. That's one. The other one is basically, it tells you more how to form things. So the other definition, too, is that given the basis vectors A1, A2, and A3. Now I'll explain what I mean by these basis vectors in just a second. Okay. Any point in the Bravais lattice can be written as, I'll call this R, I'll call this N1 A1 plus N2 A2 plus N3 A3, where N1, N2, and N3 are integers. Okay, so let's see what this means here. I'm going to draw this point here like this again. Yeah. So I'm going to pick some point. It doesn't matter really where I'm going to start. I'm going to call it. I'm going to start here. So I want to have what are called basis vectors, A1, A2, A3. Why am I not going to worry about A3? It's going to be really hard to draw it on this. That'd be for 3 dimensions. That'd be hard to do. So what I'm going to do is I'm going to arbitrarily go to this fellow here, and I'm going to call this A1. Okay. And then I'm going to call this point here then A2. Why am I calling that A2? Not that A2. No good reason. I could. Okay. If I wanted to, I could say, well, no, I really want that. I want, you know, this point here to be A1. I could. It doesn't matter which one I do. I have to come up with basically something I'm going to call it a basis vector. Now, what I'm calling a basis vector and you're calling a basis vector might be different. And that's perfectly fine. Okay. So with that said, if I want to get to this point here, what would I have to do? So these are my bases. So this point here would be what? Yeah, my N1 value would be what? 2. My N2 value would be what? 0. And you can do this with point by point. Okay. How do I get this point? Yeah.
2 and 1 minus C2.
Yeah, I need this fellow. I need this vector. What is that vector? Minus 1, A2. Now I have to add this vector, which is what?
A1.
A1. And so what would this one here be? This would be then basically this would be then this point. So this point here would then be A1 minus 1 A2. So I'd have a 1 here. And then a minus 1 here. And that's how that would. Does that make sense? I can do that from point to point. So you can think about either 2 points as being a Bravais lattice. Now, can I put in any type of points that have some sort of symmetry and call that a Bravais lattice? The answer is no. Any questions with that? So no. Not all periodic points are Bravais lattices. What's a classic case? Probably the engineers know this. We take our little handy dandy friend here. Take the one from Ashcroft and Merman, the one that you can see where I photocopied it. Turn the page. Okay. And here he has a honeycomb. Okay, here's a honeycomb here. It looks perfectly Bravais. It's all nice and nice and uniform, and it all has this periodicity. You think, oh, Bravais lattice. Okay, why would that not be a Bravais lattice? Again, now go to the first definition that is forced to erase due to the limited blackboard space in the Science Center. What was our first definition of a Bravais lattice? At any point, it has to look the same. Yeah, I'll try to convince you that even though this has periodicity, every point does not look the same. So I'm going to draw this here. So if I draw my little honeycomb. So all we're going to do is draw a big honeycomb for the rest of the semester. We're not going to do anything more. I think if you could draw a big honeycomb, then you've mastered the material. We have that. Let me try to convince you that this is not the same. So these points, this point, these points here are not the same. So let me try to do this. This would be artistic representation. Okay, so I'm going to put my hand here. And these are going to be that pair. So I should be able to go here and get the exact same thing here, right? I can go here. That looks good. Okay. But what happens if I go where? What happens if I go here? Does that look the same? No, it does not. So even though you look at this and say, oh, it has a nice, beautiful periodic structure, this must be a Bravais lattice. It is not. Because again, this point is not the same as that. So these 2 points are different. The surroundings look different. Like these 2 points. Is that still showing up? No, my. It is. Good. Okay. That makes sense? So we're just going to stick with Bravais lattices. Okay. So in a crystal, So. When we specify. Bravais lattice. Okay, A1, A2, and A3. We specify what is often called the lattice. That's your slogan. The lattice parameters. Okay, so what are, so in other words, this might be A1, this might be A2. Okay, so maybe I have something like this, A1, A2, A3. Okay, these are my Bravais lattice. I can then specify it. Often people say, well, you have the lattice parameters. So what are the lattice parameters telling you? What do you think? Again, the engineers should tell me.
A1, so A1, A2, A3.
Yeah, so the lattice parameters are going to be the length of each of these fellows here. So that'd be 3 of the lattice parameters, but then the lattice parameters give me something else too.
The angles that you.
The angles between these, and one, they're called alpha, beta, gamma, and I can never remember which is which. So the angles between these fellows here. Okay, and so basically what the lattice parameters are, there's going to be 6, but all you're really doing is specifying these. Remember the vector, the vector part has the direction in it connected with the length. So that's actually already in there. When an engineer, often a material scientist, talks about the lattice parameters, they mean really the length of each of these fellows and then the overall angle they make with one another. Does that make sense? So lattice parameters. Okay. There'll be the magnitude of A1, magnitude of A2, magnitude of A3, and the 3 angles. Alpha, beta, gamma. Between A1, A2. Okay, so they're just lattice parameters. That makes sense? What are some obvious ones we have? Okay, what do you think? So we can have cubic. So and so for cubic crystals, what do we have?
Like regular Cartesian,
Meaning,
right angles.
okay, all the angles are going to be 90 degrees. So alpha equals beta equals gamma equals 90 degrees. Okay. And then we have to be a little more fussy on this. Okay, what kind of so we have to have some sort of cubic structure. But I have a cubic structure that has different ways of writing it. What would they be?
A1 equals A2 equals A3.
Okay, so you could have the simple one. I could have simple cubic, which means magnitude of A1 equals magnitude of A2 equals magnitude of A3. That's gonna be cubic. Okay. So if you were to draw this guy here. So that'd be simple cubic. Okay. But now I want to keep the cubic part here, but then I want to tinker with it. The engineers know this well. What is FCC?
Oh,
Face centered cubic. Okay, so it's still going to be cubic, but now this is kind of tinkered with, and I don't want to deal with the length because it turns out there's going to be a couple of funky things you can do with this that you're going to work out. What would be simple cubic? And it's still the cubic one. Okay, so how does it look? What does it mean to be face centered? Yeah, I'm gonna have another, I'm gonna have basically ones on the center of all the faces, so we can also have SCC. It's gonna be face centered. Cubic. Okay, so in other words, this, when you draw it like this. And then add them there. Or point that, you're gonna put your basis values then, your stamp though. It's fine. There. Now, what I'm not gonna draw just for, because it gets too cumbersome. Yeah, the back, the bottom, and then the left side would have the same type of structure. I'm not gonna put those in because it's too complicated. Okay, then you have one other variation on this. BCC. That showing up. That is. No. This is your body centered cubic. Yeah, I'm gonna work with each of these. Well, actually, you're gonna work with them. I'm not gonna do anything. You're gonna work on all the details in the homework action. It looks all nice and cubic-y. That's fine. Then what makes it body centered? There's gonna be one right at the center here. So this is uncentered. Okay. Okay, what's the most generic one you can have? In other words, A does not equal B, the A1 does not equal A2, does not equal A3, alpha does not equal beta, does not equal gamma. Everything's screwed up.
Monoclinic?
Triclinic.
Oh,
Okay. So then you have a triclinic one, which is basically where everything doesn't equal, nothing equals itself. Often, why do you worry about the triclinic case? Because if you know that nothing is the same, alpha does not equal beta, does not equal gamma, A1 does not equal A2, does not equal A3. What can you then generate? All the other lattices just by basically letting those quantities equal each other. Okay. And then you can basically generate everything else. Okay. In other words, if I say that, if I let the alpha equal beta, if I have the generic triclinic case, then if I set alpha equals beta equals gamma, then I can start recovering all the cubic cases. Okay. That makes sense? And what can we do with these? We want to start dealing with planes. I don't think I sent this to myself. There's a dilemma here. You're going to have a daily homework 3, but you have daily homework 3 from this hand, daily homework 3 from this hand. The difference is how far I get. I just wrote on. Okay. So let's, it turns out it is useful to draw planes called Miller planes. And our lattices. So I'm just going to draw a generic. Let's just start off with a simple this and reduce a little more exotic. This is where if I don't have these all the same length, my planes are going to be really quite nasty. So I need to start someplace here. I'm going to say I'm going to start here. Okay, so this is going to be my A2. And this is going to be my A1. Suppose I want to look at this plane right here. for absolutely no good reason. Okay. The question is, how do we specify this plane? And we're going to do something weird here. What we're going to do is the planes, the Miller planes, are specified by Miller indices. And they are always H, K, and L. Okay. You only use, as far as I can tell, you only use HK now. You never use any other notation. That's why, because you don't. Okay. And what you do is you look at basically where this plane intersects your basis vectors. So to determine. H, K, and L for any plane. Okay. See where the plane intersects. The A1, A1, A2, and A3 axis. Okay. So if you look right here, where does this plane intersect this axis here? At the point, just one away. So I'll do another plane here. Let's look at this plane here too. So this is our first plane. This is our second. Okay. So if you look at the first plane, and again, I know the engineers have probably I could just give you the mark and say teach this yourself in the class and you could do it, but some of you have not seen this. Okay, so if you do the first one, never the second one. How many A1s do we go along this way before we get an intersection? One. So here basically I have one A1. Now what about the A2 one? This one here, A2. It's gonna be one. This is gonna be 1 and 2. Now if you go over here again, here's my A1 axis here like this. Where does it intersect in this one here? 2. At 2. So this would be 2A1. And this one here would then be 2A2. Okay. Now, what you do is you look at this coefficient and you take the reciprocal of it. So that's just gonna be 1/1. You take this coefficient and you look at the reciprocal of this 1/1. You go over here, you look at this coefficient, you take the reciprocal of 1/2. You go over here, take the reciprocal of this 1/2. And then you multiply these by the smallest integer that makes these numbers an integer. Okay, so multiply each of the reciprocals. Uh-oh. By each of the reciprocals, each of the reciprocals by an integer, by the smallest integer n, such that each reciprocal gives an integer. This one is very obvious. 1/1. We have 1/1. What crazy integer n can I multiply that to get an integer there? 1. The 1 here. So this right here, if I do this, this gives me the 1 and 1. These right here are the Miller indices. The first one is always your H. This one here is always your K. So this one here, you would specify by basically 1, 1. Do not put a comma when you do this and use parentheses here. Okay, so the 1, 1 here, so this would be your 1, 1 plane. Okay, now what about this one over here? What crazy integer can I use to get multiply this by to get integers? It has to be 2. So here I'm going to say n equals 2. If I multiply this through, this gives 1, 1. So hey, this is my Miller indice H. This is my Miller indice K. Hey, guess what? This one here is the exact same thing. So what does that mean? That means that each of the, basically anything that goes like this is a 1, 1 plane. That makes sense? Now, what about if I had this one over here?
Be the same.
Well, let's go through and work it out. So what's going to be our little recipe for this? So where does this intersect?
Minus 1, A1.
Yeah, if I need this guy here, so I'd have which one do I want to do? So this guy's going to be what? This would be minus 1A1. This one is
Minus 1, A2.
minus 1A2. So let's take the crazy reciprocal of these. 1 over minus 1, 1 over minus 1. This is minus 1, minus 1. And what crazy number do we have to multiply this by? This is my n. So that means I get minus 1, minus 1. So this is my H and this is my K. So this plane here would be the minus 1, minus 1 plane. Now, for reasons I do not understand, you never specify that as minus 1, minus 1. Okay. If ever you have a minus sign on one of these things, you put a bar over it. So this actually is never written like that, even though that is clear and everyone could then follow it because it would be clear. You don't do this. Instead, what you do is you always write this as 1 bar, 1 bar. Okay. But hey, what does it mean though? That's nothing but the 1, 1, 1 plane. So basically, this is going to take care of all those planes. Does that make sense? Now let's try another one. Let's try one that looks like this. What is that one? This would be our third. This would be our third zero. So where does it intersect A1? 0.
Over there.
No. At infinity. Right? This is A1. Where is this line going to intersect that? At infinity. Okay, if those of you who actually at one point when New York State, when it actually had standards. Okay. Where do two parallel lines intersect? At the omega point, the omega point is infinity. You'd say, well, wait, they never intersect there because you're not at infinity. Okay. So what do we have here? Put up where we're at. So this would be infinity, A1. And where does it intersect A2? 1. Okay, what's our little prescription say? We take the coefficient, take the reciprocal. 1 over infinity, 1 over mu. Okay, 1 over infinity is 0. So this is 0, 1, and then multiply by our value n here, and just happen to be 1. So this right here has to be the 0, 1 plane. Make sense? For completeness, this will be our fourth one. Here's our fourth plane. What is that?
Yeah, 1, 2.
Yeah, so if we go through and do this, what would that mean for the fourth plane? This has third plane. Fourth plane. Fourth plane would be what? This would be 1A1, infinity A2. This is 1 over 1, 1 over infinity, And so this would actually then give us the 1 0. So this right here is our 1 0. That makes sense. What about our fifth plane, which is this guy here? Yeah. Can't wait to find out how this works.
Yeah, so do you have multiply?
Where does it intersect A1?
2A.
At 2A1. Where does it intersect A2? 1A2. Okay, what's your little recipe? You take the reciprocal of the coefficients. Then we multiply by the smallest integer that gives us integers, which has to be 2. So this is 1, 2. So this is the 1, 2. That makes sense. Where's the 2, 2 plane? Let's ask where is. And a ballerina. Oh, sorry. Okay, so okay, where is 2, 2? Right, does that make sense? That this would be, if this is 2, 2, if I do this guy here, that has to be 2, 2, right? Oh, that's 1, 1. Where is 2, 2? I can draw it. Where would 2, 2 have to be?
Halfway between.
Yeah, 2, 2. I'm gonna use a dotted line for this. If I had this one here. If I had this one here. Okay, so I'll draw this picture here. I'll have this. Okay, so not that. So it's intersecting at the halfway point. So what would this one here be? This would be 1/2 A1, 1/2 A2. Okay, what's my little recipe say? I take those coefficients and the reciprocal. The reciprocal of 1/2 is 2. This is 2. 2. Hey, smallest energy here is 1, so this is my 2, 2. Okay, so this is 2, 2. Where'd be 5, 5? 1/5 there, right? It would be here. So they kind of behave in a little bit of an odd fashion here. You know, you think that as these get bigger, this line would actually sort of, it does not. Okay, makes sense. Now, somebody could say, moron. They're not the basis vectors, right? Somebody could say, obviously, no one would ever use basis vectors like that. So if we look at our crystal. Somebody could say, obviously, this is A1. How could it not be? Okay, but clearly, that must be A2. You know, how could you not have anything other than that? Okay, just obviously that'd be dumb. Just why would you not use that?
Make it harder for yourself.
Well, often in nature, what do you want to do, especially in physics? You look for things being symmetric. Okay, this over here, this is nice symmetry. A1 looks like A2. This over here, you know, given the symmetry of the crystal, this doesn't look very symmetric, so you wouldn't do this. Okay, but let's say you didn't know any better, or you're working with somebody who just likes to be a dick. And turns out those people exist. Okay? Another word for those are called jackasses. That's a different thing. Okay. Okay, when I was in grad school, brand new grad student, you know, all there, all bright and shiny. Since I was new, they didn't know how you'd be, so they wanted to basically put you in some place where you could do little damage, so they put you in a lab. Turns out you can do a lot of damage in the lab. But I didn't know that at the time. The first lab we had was on the oscilloscope. And they had like a zillion people taking the class, so there was an 8 a.m. lab. And so it was the third semester of physics. And so I got in there early I got in there on Sunday evening. And basically I set up all the oscilloscopes, because if you never use an oscilloscope, when you turn them on, they can do bizarre things. And I don't want to deal with that anymore. So I went in there and I set up all the oscilloscopes, all fine. What I did not notice is that the lab manager, who looked a lot like Santa, with this big long beard, bald, he smoked a pipe at that time because he could in the office. He looked just like Santa, except with Santa's jolly. He did not have Santa's jolly personality, but he noticed that I was in there. I didn't think anything of it. I went in the morning, and we'll introduce everyone, set them all, on the oscilloscopes, and every single oscilloscope was entirely screwed up. So it was a completely bizarre situation, and I mean, positions are they had no idea what happened. And he came by and went, "Yeah, I saw you there last night, setting up everything to be nice in the morning." He's like, "I want you to be able to flick on your feet." Okay, so I would put him in the jackass category. It doesn't because that's what happened. But we now have this one here. Okay, we all know that this one here has to be the 1, 0 line. Is that the 1, 0 line with that basis out there? What does that become now? That becomes the 1, 1 column. Or the 1, 1. So this one right here, if I use this basis here, again, I'd have 1A1, 1A2. I take the reciprocals, and this gives me the 1, 1. So this is the 1, 1 plane and this basis vector. And if I use these basis vectors here. So what you call a Miller indice, what you call the Miller indices here depends entirely on the basis vector you use. Okay? What would then this line here be? This would intersect at 1A1. Where does it intersect this A2? Infinity. Infinity A2. I take the reciprocal here. This is 1, 0. So this would be the 1, 0 plane in the set of basis vectors. Does that make sense? Okay. Now we're going to start doing some things which again it gets a little on the convoluted side. Let me kind of set up some things just so you know what's going to happen here. So why do we care about Miller? For one, it tells us a plane. So obviously it gives us a plane. It gives the Miller plane. And we don't know why that's useful yet, but when you do Bragg diffraction, that's going to be an X-ray scattering, and that's going to be all we need now. Okay. But two, the quantities H, K, and L give us, allow us to calculate a new vector called G, which is perpendicular to the Miller plane. What that means here I have, so let's say these are my 1, 1, 1 planes. I can actually make a vector here like this, call it G. And that G, if I know what these numbers are here, I can construct this G based on this Miller indices here. And this would be perpendicular. Further, if you look at the magnitude of this G vector, okay? Actually, if you look at 2 pi, or the magnitude of this G vector, this is equal to the separation distance between these two. So this D here. So this D here, this is your separation. the Miller planes. Okay, is given by, and it should say it's the perpendicular separation distance between the Miller planes. It's given by 2 pi over the magnitude of this g. Now that's not one but obvious, and what I want to do today and on Tuesday is to show you how this is going to work. Okay, I'll show you what the g is going to be specified by. It's going to be kind of weird, but this is what we're going to talk about today and then going into Tuesday as well. So I have not proved that statement at all. I've clapped my hands and stated that thus we will show. Well. Just so you know, this is never done in this class. Again, since I want more engineers to take this course, and I know I actually sat in on the spectroscopy class, then Dr. Mister's X-ray class. I know you need to know this in detail. I don't know if the why it works is done in your other classes. Maybe it is, but I'm still doing the why it works part. Yes.
Is that D, like the distance between the
Any two adjacent planes here.
planes, that's for like the XRD stuff, right?
Exactly. So when you get your XRD information here, it is this
That's the
D.
D,
It is
yeah.
this D. I want to show you how it's related to the HKL. See, you've had X-ray, right? Or in there? Okay, well, you can XRD. Okay, this is where it's coming in. Okay, it's going to be used. Okay. So we will see. Okay. And here's that the G vector is given by G equals H B1 plus K B2 plus L B3, where B1, B2, and B3 are called the reciprocal. You know, I'm gonna have to go on how to spell this. Reciprocal.
I know.
Reciprocal lattice vectors. Okay. So what I want to do right now is show you how you start getting these B vectors. And again, so we're going to get these word B vectors that seem stupid. Okay, well, why would we even care about these? Okay, we're going to care about them because basically, if you know the Miller indices and if you know this B vector, you can then determine the separation distance between these planes. And when you do X-ray diffraction or many types of scattering, by knowing what the D's are, you can actually then start. You can start then putting the crystal together. What kind of the actual structure of the crystal. Okay. This makes sense where this is going. Okay, so the question is, what are the B's? How do we define the B? So, by definition, the B vectors are perpendicular to the plane containing any two A vectors. Okay. So let's say I have an A1 like this. I have an A2 like this. The two vectors here. I want to have a new vector and I'm going to call it B. And I want that B vector to be perpendicular to this plane. It could be perpendicular this way here. It's ultimately not going to. Okay. But I want a B vector by definition to be perpendicular to this. Okay. So we want B, I'm gonna call it B3 to be perpendicular to the plane containing A1 and A3. So first of all, why are we calling it B3 and not B1 or B2? Just from a pragmatic point of view.
I would think if you called it like B1, you might get it confused with A1. Like,
Yeah, so in other words, let's say you call it A1. Well, why aren't you calling it A? I mean, what if you call it B1? Why aren't you calling it B2? What's special about one of these two? It's not. So since we have a 1 here, we have a 2 here, the next one we're going to define to be B3. Okay. If I had a 2 and then a 3 here, what would then my B vector be? 1. And again, if I then have a 3 and a 1, I'm going to have B2. Okay. And you've all had physics 1, and you've had physics 2. So tell me how, and you've also had calc 1, 2, and 3. You tell me how we're going to have to start doing this. I want to create something that's perpendicular to these two vectors. And you all have a friend. What is the friend? A cross product. So what we're going to do, we're going to say that B3 is proportional, because it turns out there's going to be some weird things we're putting in here. Okay. I'm going to say that this is going to be A1 cross A2.
Is that supposed to be A3 down there?
Okay. Shannon wants correct notes. Okay, so when you see me doing something moronic, call me on it. Thank you. Okay. Everyone say that this is stupid. Okay. But watch what I can do with my finger. A superpower. No, that'll work. Okay. 2. Okay. It doesn't squeak well. It's Batman losing his utility belt. Okay, again, thank you. When you see me do something stupid, call me out. Okay, so we have this right here. What would then be B1? I call this A2 cross A3. And then tell me about B2. So that's going to be A3. I'll try to convince you why. Cross A1 like this. Okay, the way you remember this is put 1, 2, and 3 in cyclic order. So here's 1, 2, and 3. What does it mean to be in cyclic order? So if I take this 3 and put it here, what do? I take the 1 and move it over here, and the 2 and put it over here. Look at this. If I take the 2 and put it over here, what do? I move the 1 over here and the 3 over here, so I get this. So put the 1, 2, and 3 in cyclic order. Okay. Now, what are we going to do? Okay. The actual definitions. Of B1, B2, B3 is, I'm going to say that B1 is going to be 2 poly A2 cross A3 over the magnitude of A1 dot A2 cross A3. And all I'm going to do is I'm going to take this factor here. And I'm going to put them in front of each of these here. There's a reason why we're doing this now. I'll explain why. Okay, so this actually specifies in which homework you get in. So let me get this out, hand in the homework. So that, let's go on this on Friday. We're going to go Tuesday. We'll limit that. Basically, Tuesday goes back in time, bounces off Friday and goes to Tuesday. So then this is in 2 pi times A3 plus A1, or magnitude is A1, not A2 plus A3. And then B3, same thing. Okay, so I'll explain why we want that. It's not obvious right now, but you get a brand new shiny illegitimate frame. It's just doing Miller indices. And it's basically, it's this, just with, that's just doing Miller indices. And Bravais lattices.
Hey.
You're welcome.
Remember when it's not a man, it man. When we. What it was more. I mean, yeah, I don't really use it at all, right? I mean, yeah, there's a lot of qualified, but.
Or more.
Three times, no.
Three house.
So many.
And it was never talked.
Yeah, I think business where we are.
I'm good again.
It appears as though it was here, which was limited, but would appear now.
It's just.
Sorry.
Oh, you're fine.
You haven't talked about.
Oh no, it went flurry.